Hey everyone, welcome to this week's me lecture. Today we're going to be covering chapter 9 from the textbook. And so essentially during the past few, months in 170, we've covered a bunch of algorithms, right? Dynamic programming, graph algorithms, etc. And for each of those algorithms, we had some sort of problem. We chugged it through our algorithm and we got a clear-cut solution to them, right? We knew that solution worked and it was like the optimal solution. But during the last few weeks, we've talked about NP-complete problems, where we don't really have an efficient solution to solving these problems, right? We don't really have a smart, efficient way of getting to the optimal solution. And so the only solution that we have is an exponential search, right? Trying out every single possibility available to us until we find the right answer or like the optimal value, right? And so in the real world, having these exponential algorithms is just not, feasible, right? It doesn't make sense. We're going to need to come up with a better way of, if not like, completely tackling these NP-complete problems, we want to figure out some efficient way so that we can at least like deal with them to some extent, right? And so today we're going to be covering three main approaches to doing that. The first is, and it's called the intelligent exhaustive search, which is, I believe, 9.1. Yeah, check out the textbook again, chapter 9. It does a great job in covering these concepts. But again, today, like in this video, I'm just going to be covering like mainly the intuition behind three different approaches. And at the end of this video, we're going to be covering, I believe, 2 or 3 example problems that make use of some of these approaches. So if you want real examples, skip toward closer toward the end of the video. But anyway, moving on to the intelligent exhaustive search, right? So the example we'll look at is 3-SAT, which we know is an NP-complete problem. We don't really have a good way of finding the solution to the problem other than simply trying out every single possible combination of assignments, right? And so the one strategy that we have is called backtracking, where we assign some values, and the moment that we assign a value and we see, hey, assigning this variable this value is gonna break the entire expression, then we stop and go back. And so kind of more concretely put, let's say we have this example list of expressions that we want to and we want to find the appropriate assignments to make all these expressions valid, right? And so, for example, we can, let's kind of like visualize it in terms of like a graph structure, right? So how backtracking works is, all right, let's first assign W, right? So we have 2 options to assign W. We can either assign W to being 0, where 0 is false and like 1 is true. We can assign W to equal 0, or W can equal 1, right? So now what can we do? The moment we assign W equals to 1, what we do is we plug in W equals 0 into all of the expressions, say, okay, does this break any expression? If it does, immediately, don't explore any more variable assignments where W equals 0. And so kind of to make that more concrete, so we have W equals 0. If you plug in W equals 0, since it's just one variable assignment, it's not going to break anything just yet. But so let's assign the next few variables. Let's go with, let's say X. So let's assign, again, for X, we have 2 options, either X equals 0 or false, or X equals 1, aka true. And so let's look at this, this node, right? Where we've assigned W to equal 1 and X to equal, where we've assigned W to equal 0 and X to equal 1. If you plug in W equals 0 and X equals 1 into these, the list of these expressions, what we're gonna realize is that immediately breaks the expressions. And the expression that it breaks is this one. So if we plug in W equals 0, we'll have a 0 here, and X equals 1, and we take a naught of that. So this will also be 0. So this entire expression becomes 0. And again, the whole three-step problem is we want to make sure that each of these expressions is true, right? So the moment that we find out that, the assignment of w equals 0 and x equals 1 invalidates one of these expressions, in this case it's this one, then we stop there. We don't keep exploring this subtree, right? Because otherwise the next logical step would have been to do, for x equals 0, let's assign y next. So the two possibilities for y are y equals 0 or y equals 1. And we would have done the same thing here. Oops, sorry, it's kind of messy, but we would have done the same thing under, this branch, right? But instead, the moment we see that w equals 0 and x equals 1 doesn't work, we don't have to explore this subtree anymore, right? We can basically prune that entire subtree out. So instead, we can just basically not even explore those options and say, okay, done, not a solution here, right? So basically what backtracking is it's like a nice way of making your algorithm a little bit more efficient by pruning out potential solutions that we know won't work, right? We're essentially pruning the entire potential solutions graph for any solutions that we can easily tell in advance won't work, right? So instead, like moving on, we can explore, so c equals 1, and et cetera, et cetera. We can do the same for here. And again, anytime the moment we see some sort of assignment that doesn't work, we don't have to explore any of the ones below it, right? That's what pruning is. So again, to kind of reiterate, what our normal, like, kind of basic solution would do would be the exponential way. Since we have 4 variables here, w, let's say w, x, y, z. For each of these, assign, we can do true, true, or let me use ones. 1, 1, 1, 1. Another solution can be 1, 1, 0, 0, 1, et cetera, et cetera. And there's going to be, again, like 2 to the 4 of these, right? So it's going to be exponential. This is the, kind of basic way of solving this. What backtracking allows us to do is, instead of like looking at entire sets of the possible solution, in this case, if we have a potential solution that is, 0, 1, something, something for y and z, the moment we see a 0 and 1 for w and x, we don't have to explore the rest of the solution. So that's what backtracking is. And this is kind of like, again, straight from the textbook. This is, what the entire graph, this is what the entire solutions graph looks like after we've done all the pruning. As you'll see in a normal exponential search algorithm, what you would see in all these graphs is there wouldn't be any pruning, right? So all of these nodes would still exist. And same for here. So as you can see, there's a lot of solution nodes that we don't even have to look at by pruning. So yeah, that's what backtracking is. And branch and bound is like a very similar method. I think it's covered in 9.1 as well. But it's more for optimization problems where we're trying to find where we're trying to minimize or maximize some sort of cost or value function. So yeah, that's the first approach, intelligent exhaustive search. The second approach is called approximation algorithms. And essentially, kind of the use case with approximation algorithms is, let's say, hey, we have like a problem in the real world that we know is like intractable, right? Like, let's say we don't have an efficient solution to solve, to tackling it. But let's say for this particular problem, we don't really care about finding the absolute best answer, right? So maybe let's say our problem is just like a basic, basic problem. Let's say we're trying to find like the best way to get from here to like, I don't know, some other point, like let's say like Colorado or something. And we're trying to minimize like how much gas we use. Let's say we don't care about like, hey, I don't really care about using the absolute minimum amount of gas. Let's just say I want to use like, I don't want to use like too much gas, right? So anytime you don't really care about finding the absolute best solution, whether it's a minimization or a maximization problem, we can use approximation algorithms. And essentially what approximation algorithms allow us to do is we can find a solution that's pretty close to the actual, like the best solution, but it's not exactly the best solution, right? So to be more specific, how we analyze these types of algorithms is we define, several variables, right? The first one is called OPT of like I, it basically represents the cost associated with the optimal solution. And again, I represents like the instance of a problem, right? If any of these like definitions like I or NP completeness are like iffy, please check out like previous, I think it was last week or 2 weeks ago, mini lectures. So yeah, the optimum of I represents the cost associated with the optimal solution, so problem I. What A of I represents is the cost associated with our particular solution to problem I, right? So let's say we come up with an algorithm. So again, to reiterate, in this case, we're dealing with a problem that we don't have an efficient solution to. But let's say we came up with some sort of algorithm that's really efficient, let's say like linear time, for example, but it doesn't guarantee finding the best possible solution. So for that problem, for that algorithm, A of I represents the cost associated with our particular algorithm when it's run through, some sort of problem I, right? So again, this is the best possible, and A of I is our answer, the cost associated with our answer. So the value that we care about is the ratio between them, essentially, right? So this ratio is going to tell us how far off we are from the optimal value. And again, to kind of make it really clear, this is for a minimization problem. So you can kind of like think about an example for a problem, right? Let's say we have some sort of NP complete problem, and let's say the optimal solution like out there, or like the actual optimal solution for the problem is, let's say it's like 5 or something. And let's say our like efficient algorithm that we have, but it's an efficient approximation algorithm, gives us an answer of like 15. So then what we're going to care about is like the ratio between the two, right? 15 divided by 5 is going to be 3, right? So then we say our problem or our algorithm is a factor of 3 away from the optimal solution. And the reason, we have this extra term of like maximum over I is that, so essentially we're given some sort of general problem, right? Let's say it's like the TSP problem, the traveling salesman problem, and we're trying to minimize something. Or let's say it's like Euler path or like the Rodrada cycle. Anytime we're trying to minimize some sort of value, we don't care about a specific instance of the problem. What we want to analyze instead is for any instance of that problem, like let's say Rodrada cycle, for any instance of that problem, we want to figure out what is the maximum possible ratio that we get, right? So essentially what this maximum, what this term is doing, like taking the maximum of all the possible ratios is, we want the maximum possible ratio. It's basically on like the worst possible input, right? And what this essentially means is like, let's say our algorithm does an incredible job for 99% of the possible input, problems, right? Possible instances of the problem we're analyzing, right? But on 1% of the problem, of instances of the problem that we're looking at, let's say our algorithm is like terrible, right? Let's say it's off by a factor of 10 away from the optimal value. Then our, our factor that we're, our factor that we're going to return is going to be 10, right? We care about how our algorithm does on the worst possible input, not just on any random input. And so that's why we take this max over all possible instances of the problem. So yeah, that's for a minimization problem. For a maximization problem, our factor, the factor that we're off is going to be the exact same, except we've taken the reciprocal. And if you like kind of like think about logically, like let's say our optimal value, like for a maximization problem is like 15, right? So let's use a different value. Let's say it's like 50, and our algorithm returns, a maximal solution that is like, let's say 25. Then we'll say, the factor that we're off by is 2, right? So for a minimization problem, it's our cost divided by the optimal cost, whereas a maximization problem, it's the optimal value divided by our value that we get using our algorithm. So yeah, that's kind of like approximation. That's kind of like the gist of approximation algorithms, where we don't care about finding the absolute best answer. And we're going to be covering like one example problem using approximation algorithms. But anyway, moving forward, the last approach that we have is called local search heuristics. And so the overview for local search heuristics is basically, the first step is let's choose some initial, kind of like random solution that we have, right? So for a minimization problem, for example, let's just choose some like solution. We don't know whether it's good or not. We just kind of like arbitrarily chose it, right? Step number 2 is going to be, all right, scan neighboring solutions. And what I mean, like when I say neighboring, I mean solutions that are like pretty close to the solution that we initially chose, but like maybe off by a little bit, like different by a little bit, right? So let's say we have like a bunch of like edges or like cycle in a graph, right? Why don't we change like a couple edges on the path? It's basically like tinker with our current solution a little bit to come up with another solution, but that's slightly different. So that's step number 2, right? So scan for all the possible like neighboring or similar solutions. Step number 3 is if one of those neighboring solutions, passes our criteria, which I'll get to in a bit, then we'll like hop over to it, right? So kind of like jump to that neighboring solution and go again, right? So let's say basically like visually speaking, like let's say we start off with like some solution here, and let's say there's a neighboring solution like S prime, right? That's like off by maybe a little bit. It's like different from S by a little bit. So, and let's say it passes our criteria, we jump over to S prime, and then we do the same for S prime, right? Find some sort of neighbor of S prime that's similar and also passes our criteria. Let's say that's like, I don't know, S prime prime. Then we hop over to S prime prime. And then we keep going, iterating through neighboring solutions until we found, some sort of solution that doesn't have any more neighbors for itself. Once we have that, we just return that. And so this is why it's called local search. It's because we're only looking at like neighboring solutions, right? Solutions that are pretty close to our solution that we have right now. They're just like different by a little bit. And so what do I mean by like passes our criteria? You can define multiple, like there's multiple ways of defining your criteria, right? One possible definition is saying, okay, only hop over to a neighboring solution if the neighboring solution has a lower cost than our current solution, right? So let's say we're like searching through a path in a graph, right? And we have some sort of path that has like cost of like 20. And we've like tinkered with our current solution a little bit. We've maybe like played around with a couple edges, and we've come up with another solution with cost of like 15. One possible way of defining our criteria is saying, okay, since 15 is less than our current solution, which has cost of 20, let's hop over to that solution. And so we hop over to that solution, then tinker with another couple of edges, see if there's any neighboring solution to that that has an even lower cost than 15, and keep kind of like iterating through that process until there's no possible neighbor that passes our criteria. And so that's kind of like one possible way of doing this, right? And so if we have like a minimization problem, let's say like this is, you know, this is an example for like our cost function, right? That we're trying to minimize. So basically it's kind of like looking over, you know, checking any neighboring solutions, seeing if they're good. Are they good? If so, hop over to it and get those neighboring solutions. So that's kind of like local search heuristics, right? Now there's a couple ways of playing around with this a little bit. And in fact, I used local search heuristics for my 170 project when I took the class. It may or may not be useful for you. But anyway, so in the way I approach, in the approach that I stated earlier, our criteria was, does the neighboring solution have a lower cost? If so, move to it. Another way of defining the criteria is, so there's actually a problem with that approach, right? So let's say, step number one is choosing some initial solution, right? So let's say our initial solution, we chose right over here. And, one possible neighbor that we get to is, let's say it's like over here, right? And we say, okay, let's say this has cost like 25, and let's say this has cost of 20, right? So we start off with this solution and we check the neighboring solution S prime, and we see, hey, it has a lower cost of, S prime is equal to 20, therefore we move to it, right? But once we get to S prime, we check our neighboring solutions, right? So let's say we check, this value and this value. Let's say this has cost like 24, this has cost 23, right? We check the neighboring solutions. In this case, both of the neighboring solutions for S prime are greater than the actual solution for S prime, right? So S prime is only cost 20, but the neighboring solutions have cost 23 and 24. So we basically return S prime at that instant. But as you'll notice, if you look at the rest of our cost function, you'll see there's a very good, solution that's just a little bit away from S prime, but we didn't really analyze it because we only looked at the immediate, neighboring solutions of S prime, and we only move to a neighboring solution if that solution has a strictly lower cost, right? So what that led us to doing is missing out on this amazing solution of, let's say, like cost 5, right? And that's kind of like getting trapped. That's a result of getting trapped in some sort of bad local optimum, right? So this is some local optimum, whereas this would be the global optimum, right? And our whole like kind of mission is to improve, make our chances of finding the global optimum as large as possible, right? Let's try not getting stuck at some bad local optimum. We want to find the global optimum potentially. And if we don't find the global optimum, at least, at the very least, we want to find a good local optimum, right? So to kind of like overcome this problem, what we'll, do is called simulated annealing. And what this means is essentially, okay, look at the neighboring solutions. If it's better than our current solution, all right, go to it. But if it's worse than our current solution, instead of completely ignoring it, assign some sort of probability to it. So let's say in this case, right, we were at S prime and we're analyzing our neighboring solution of 24, right? 24 is like 4 off from 20, which isn't that much, right? So assign some sort of probability that we hop from S prime over to, the solution, I'll call it like S double prime. So maybe like, I don't know, and that probability can be arbitrary. I think the textbook uses some sort of exponential probability, which might be a good systematic value. But the kind of like general intuition is saying, okay, if we explore a worse solution with some probability, so like, let's say, with some probability, like let's say 10%, right? There's a 10% probability we go from S prime to S double prime. And if we go to S double prime, now we have the potential of exploring, of getting to this actual actually really good solution, right? Because from S prime, from S double prime, a neighboring solution could be this, right? This value right here. And a neighboring solution for that could be here, and et cetera, until we get to our global optimal value, right? So the whole point of like doing simulated annealing is to not get stuck at some sort of bad local optimum, to give us a chance of exploring, because a bad solution right now might lead to a better solution moving forward, right? Because like exploring the, S double prime with the cost of 24 would lead us to also potentially exploring the global optimal solution, which is what we want, right? Whereas if we have a strict definition, and say only go to a neighboring solution if it strictly has less cost, um, you know, that might get us stuck into some sort of bad local optimum. So that's kind of like the concept of local search heuristics. I believe it's section 9.3. But yeah, those were 3 approaches to tackling or coping with, NP-complete problems. See you guys next week.
Hey everyone, welcome to week 12 of recorded mini lecture, and I think by the time you guys watch it, it'll be week 13. So hopefully people are excited about the end of the semester, and yeah, so I don't know, thoughts aside, let's jump right into today's topics: modular exponentiation and primality testing. So both of these topics are very special because it differs a lot from the sort of viewpoint that we've been taking for the past, I don't know, however many weeks. Because in the past, we've sort of glossed over the idea of arithmetic. We've said, oh, like dealing with constants is easy, multiplication can be regarded as constant time. And you see this like on your exams, in your exercises all over the place. But is it really like, do we actually have really simple ways to do these things? Do we have very efficient algorithms for multiplication, exponentiation, all that good stuff? And maybe you've also heard in the past that primality testing and multiplying numbers are easy, but then factoring is not, in the context of cryptography or stuff like that. But today we're going to dive really deep into the actual arithmetic underlying these operations, and giving some efficient algorithms to aid us in being able to keep making these horrible assumptions about really important arithmetic going forward. All right. So just as a reminder, when we're doing modular arithmetic, we're saying that, two numbers, x and y, are the same, mod n, if and only if they differ by some integer or multiple of n. So k is an integer. Right? So the way I like to think about this is that by identifying any pairs of numbers that differ by a constant multiple of n, we're shrinking the number field. Instead of having infinitely many numbers as we're used to in the integers, we now can say that all of our numbers are essentially smaller than n, because given any number bigger than n, it's equivalent to something that's smaller. So we might as well throw them out. Right? So you're probably familiar with this from FFT exercises in probably previous classes, so I won't go too deep into this. If you're unfamiliar, I encourage you to go to the textbook or find some source. There are a lot of awesome sources to touch up on modular arithmetic. All right, so let's do addition now. How do you do addition in modular arithmetic? Well, you might be saying you just add normally and then mod. And that's perfectly right. So you add normally, and then you take away copies of take away copies of n, you shave off copies of n until you get something that's smaller than n. Right? And this is an okay thing to do, because if I take two numbers x and y, both of which are mod n, so both of them are smaller than n, when I add them, even normally, I'm going to get something that's smaller than 2 times n, right? And so the worst case scenario, I have to shave off an extra copy of n, and we're done. Sometimes you don't even have to do this step. So worst case scenario, you just have to do one more step shaving off of n. So as with regular addition, this is going to be linear time. And let me just make a note here that linear time on n, this n and this big N are different. This n is the number of bits in big N. So this is the length of the number. in this entire discussion of arithmetic, we'll always want to analyze runtime in, I guess, in language of the length of numbers. We want to do runtime as a function of the length of numbers, number of bits in that number. And this is as opposed to, taking the number itself. And this is essentially just, this is going to propagate throughout this entire mini lecture, so make sure you remember that I'll probably ramble about this multiple times going forward. All right, so what about multiplication? Same thing, right? You multiply normally and then shave off copies of n until you get something that's smaller than n. That's going to be mod n, right? And then when you're multiplying two numbers that are smaller than n, you better get something that's smaller than n squared, right? And then, so worst case scenario, you have to shave off on n squared copies of n. You have to shave off like n copies of n. Worst case, right? Not too bad. So again, this extra work isn't going to really, drastically modify your runtime. You're still going to get an n squared runtime as with regular multiplication. And this is, again, n is the length of your number n. It's sort of just log base 2 of n, right? Because we always operate in base 2. Okay? All right. So division is a little bit more problematic because, as you remember, in regular arithmetic, we can't divide by 0. And so 0 is the only one that's problematic in our regular number field. But in this case, we're actually going to run into a few different problems. So let's consider this example. This is, the classic example is, can you divide by 3 in mod 6? And the idea of dividing by a is the same thing as multiplying by a inverse. And this is just because we understand multiplication really well. We already know how to multiply. We already know how to execute multiplication. So we want to formulate division as a byproduct of multiplication. So dividing by a is the same thing as multiplying by a inverse. A inverse is just some element, also mod n, such that when I multiply a with it, you should get 1. Right? So essentially for each a, you would like to find an a inverse. And for a regular number field, probably over the integer z, you can say if a equals 3, then a inverse is just 1 over 3. So on and so forth. The only number that doesn't have this inverse is 0, right? Because you can't take 1 over 0. However, over a different field, over a different mod n, you might have numbers that don't have a multiplicative inverse. For example, 3 mod 6. You can go home and try this by hand, that take any number mod 6, so 0, 1, 2, 3, 4, 5, and multiply to 3 mod 6, you're never going to get 1 mod 6. And this is problematic, because essentially, if you can't multiply by a inverse, because there's no a inverse, then you can't divide by it. You can't divide by a. Right? So this is a problem with zero divisors. If you're interested in this, group theory is a magical subject. You should look into it. But essentially, this is a little bit more problematic than addition and multiplication. But at the end of the day, it's going to be polynomial time, and the book explains better. So it's O of n cubed. All right. So again, n is the length of the number. We've gone through addition, multiplication, division, and now we come to the last one, or I don't know, the namesake of our lecture, exponentiation. So exponentiation is a little bit different now, because in the past we've always been able to just do the operations normally and then do the mod thing by shaving off however many copies of n as you want. However, you might already see this, that this is not going to be the case with exponentiation, because exponentiation or exponentials grow very, very fast. There's this whole story about a king who lost his entire kingdom by placing twice the number of grains as the previous, on a chess grid. I don't know the story exactly by heart, but if you're interested, there's this, parable that you should never gamble with exponentials. So the idea is that exponentials grow very, very fast. So if you do this exponentiation normally, then already you might be getting this humongous number that you can't even store in your machine, let alone start shaving off copies of n. So the naive approach to solving this problem is, well, okay, every time I multiply a new copy of x, I'll mod n, right? So this way, every time after I mod n, I will get something that's smaller than n. So to illustrate this, we'll just say, okay, I take x and then I multiply by x, I get x squared, multiply by x again, x cubed. This is literally unpacking the definition of an exponential, right? And you get all the way up to x to the y. And at each step, we're going to mod by n, right? And this is going to be the same idea as multiplication, because you can sort of induct that every time you do this operation, your two numbers are multiplying your x to the n and your new x will both be mod n. So you're going to get, squared n squared time multiplication, right? Okay, so each step is fine, but here comes the real bummer: is how many steps do we have to take? You might be thinking, oh, it's just y steps. But remember, we want our runtime to be in terms of the length of numbers, right? So what if we said n is the length of y, right? What if I said n is the length of y? Then the number of operations is going to be 2 to the y, right? Because the length of y, n, is going to be log base 2 of y, right? So this is already problematic. You can already see that whenever we have an exponential runtime, we should go and find ourselves a better algorithm, right? Because when we formulate this in terms of the length of our exponent, we get this horrible runtime. So we have to, make this less naive in some way. And the way we get around this is instead of multiplying by a single copy of x, we're going to multiply by however many copies you have right now. So each turn, we square the current number. So we start with x, we go to x squared, and then we go to x to the 4th, and we go x to the 8th, the 16th, so on and so forth, so that you can see that now we have fewer operations until we get to something that's close to our y, right? So essentially, we're trying to bypass the problem of having too many operations. So where do we end? We start squaring up until we get this number, 2 to the floor of log y. Pause the video right now if you want to think about what this number means. All right, hopefully you're back. This number is the largest power of 2 that's smaller or equal to y. Right. So at each step, we get some x to some exponent where the exponent is some power of 2. And then we don't want to go over y, right? We don't want the exponent to go over y because it'll be pretty useless. So we stop at the largest power of 2 that's smaller or equal to y. And you might be thinking, okay, I get this idea of like you don't want to go over, but if you start at the largest power of 2 that's smaller or equal to y, if it's smaller than y, how do you get up to y? Great question. We're going to address that right now. So think about how to make y from all of these components that we have a handle on. Essentially, after we do this string of computation, we now have a handle on x squared, x to the 4th, essentially x to any power of 2 that doesn't go over y. Right. So how do I use these building blocks to build x to the y? I encourage you to pause the video right now and think about this. All right, hopefully you're back. I hope you're not cheating me and not pausing and just, going straight through. But here's the thing, right? Remember, if I can make y, essentially I want to make y as some sum of these 2 to the i's, right? What does this mean? Essentially, we're trying to multiply together a bunch of x to the 2 to the i's so that we could get x to the y. Remember how when we're multiplying, the exponents add. So essentially all we want is some number of 2 to the i's that adds up to y. And this should immediately make you think of binary representation of y. The entire idea of binary representation, binary representation of y is just a decomposition of y into different components that are 2 to the I. So for example, if I have 9, then I have, 9 is equal to 2 to the third plus 2 to the zeroth, which makes 1, 0, 0, 1. Okay? If you're not familiar with binary representation, I encourage you to read the textbook or brush up on that. It's a fairly straightforward idea, and it'll help you understand this. All right. So now that we've written y as the sum that we desired, now we can just multiply all of these things, but as exponents, right? We have a handle on x to the 2 to the I for different i's. And now if we just multiply all of them, we're going to get x to the y because the exponents add, right? Okay, so let's look at runtime. To calculate this entire building block, the sequence of building blocks with exponents to the I, each arrow's operation, so each squaring operation is going to take O of n squared time, where n is the length of n, right? Because so essentially every single number is going to be mod n, so it's going to be smaller than n, and then by the multiplication criteria that we talked about just now, the runtime is going to be n squared. Okay, and how many operations are here in total? Well, okay, it takes 1 operation to get to x squared, 2 operations to get to x4, 3 operations to get to x to the 8, 4 to get to x to the 16. It's not hard to see that it takes k operations to get to x to the 2 to the k, right? So how many operations are we looking at in total? It's O of log y, right? O of log y. Remember how we had this problem before where we had a runtime of 2 to the y. Now we don't because we're going to take a log of y, right? Oh, sorry, this is log 2 to the n. Huh, whoops. Okay, previously we had just 2 to the n, but now we have log of y. So you can check at home that this is in fact going to be polynomial time. And then this sort of constructing y out of these building blocks is also going to be polynomial time. So when we add these steps up, it's going to be polynomial time. So this is a much better approach than what we had naively because we've drastically reduced the number of operations that we have to do in the number of multiplications we have to do in order to get to x to the y. Okay, so another viewpoint of this is, instead of building from the ground up, squaring, we can sort of look at it as recursion. So what do I mean by recursion? If I want to calculate x to the y, all I have to do is just sort of go one level down. I want to get something that squares to x to the y, or something that squares to almost x to the y. This might be a little bit vague, so let me just write what I'm trying to say down. This is equal to x to the y over 2 floored squared, right? So now all we need to calculate is going to be x to the y over 2 squared. And that can be calculated by dividing by 2 again, dividing by 2 again, and again and again. And you'll see that this recursion is going to be log yd. Okay? Now, if y is odd, then I can just make it even by pulling out a factor of x. And now what's inside is still x to the y over 2 floored squared. And the reason I can still keep this floored is because, well, if y is odd, then y over 2 floored is going to shave off an extra copy of x than we intended. It's like the idea of saying 5 divided by 2 floored is 2, 2 times 2 is 4, but then there's an extra 1 until we get to 5. Okay. So here's an exercise to check at home. Check that this is the same thing as above, or the same idea as above, right? And then another thing to check is that it reduces to the base case of above. Okay, so it reduces to like x and x squared. Awesome. All right, so that concludes our discussion of trying to find an efficient algorithm for exponentiation. Just to recap, our naive approach of just multiplying another copy of x one at a time failed because the number of operations that we're doing is exponential in the length of our exponent. Okay, and we fixed this by squaring each time so that we don't have to do as many operations. We're doing basically a log of the number of operations as we did previously. Okay, and then at the end we reformulated this algorithm as recursion. Okay, so in the next segment we're going to talk about Euclid's algorithm as well as primality testing. So stay tuned for that. All right, let's talk about Euclid's algorithm. So Euclid's algorithm is an algorithm for finding the greatest common divisor of two numbers a and b. So I input two numbers a and b numbers. Let me change the color. And I want to output the greatest common divisor of a and b. So think about how usually you calculate greatest common divisors. For example, if I want to calculate the divisor of say 12 and I don't know, 16, then I might just write down the prime factors, prime factorization for each. Say, okay, this is 2 squared times 3, this is 2 to the 4th, and I take however many copies of these prime factors as I possibly could. So in this case, I could only take 2 to the 2 squared, which is 4, and I have this is the GCD of 12 and 16. So you can imagine, this is a fairly, harmless way of doing GCD. However, if you can imagine that this could get very problematic if you have huge numbers. If I hand you two numbers, say 976 and 754, I'm sort of just making these up, but essentially, if you have humongous numbers, it's going to be hard to factor them into their prime factors, and we already heard about this. Factoring is very hard. So this is not a great way. So we want to get around this, and the way we get around this is by the state-of-the-art Euclid's algorithm. So here's the algorithm. The way it works is if b is equal to 0, so this is the base case, we return a. This essentially says that the greatest common divisor of any number with 0 is just that number. There's no tricks to it. Otherwise, I'm going to recurse. I'm going to take Euclid of b and then a mod b. Okay, so this is a little bit mysterious. Why the heck are we doing mod? Like, where did this mod come from? Here's the theorem that motivated all of this. The theorem says that the greatest common divisor of two numbers x and y is the same as the greatest common divisor as the number x minus y and y, right? So the idea behind this is, if something divides both x and y, it better divide x minus y as well. And you can check this at home, right? And so the idea of modding by b is just say, I shave off as many copies of y as I can without getting x to be negative. So I can say that you do this repeatedly until you get GCD of, I don't know, x minus ky and y. And to ensure that the smallest component is always on the right, we make this GCD of y and x minus ky. And in the end, we'll just get, Euclid b a mod b. Okay, so this is the theorem that motivated all of this. I guess this is Euclid's lemma, Euclid's theorem, whatever you call it. And essentially, this proves the correctness of this guy. And because every turn, this right side is going to decrease because it's going to get modded by a smaller and smaller number, eventually it will get to the base case where b is equal to 0 and will return. Okay? All right. So this is calculating the greatest common divisor, but we want to do more. Why are we doing Euclid's algorithm in the middle of this discussion between, modular exponentiation, modular arithmetic, and primality testing? There's actually a slightly deeper reason. So there's this lemma that tells us that if D, if D divides two numbers A and B, and D is equal to some linear combination of AX plus BY, then I better have that D is the greatest common divisor of A and B. So this is I don't know, it looks like someone just pulled it out of thin air, but you can convince yourself of this, or you can read about it in the textbook. It's a very beautiful thing. Essentially what this says is, if you have this, once you have this greatest common denominator, you can take linear combinations for A and B to make that, to make that greatest common divisor. And this is, I don't know, this is not obvious to me when I was learning this. For example, that in particular, example, if I have that A and B are co-prime, then necessarily I have some, I don't know, some linear combination AX plus BY that makes 1. Okay? It's not always clear that if you have just, I don't know, two co-prime numbers and you do some linear combination, you always get 1. But the reason we're really excited about this is because, look at this. This means AX is equal to 1 mod B. Does that ring a bell? Like, does this statement ring a bell? Well, it should, because back at the very beginning when we were talking about division, we said that we wanted some I don't know, some inverse such that if I multiply this inverse by A, I get 1 mod N, right? So this tells us that if we're doing stuff mod B, then A and X are multiplicative inverses, and this gives us grounds to do division. So we're very excited about this idea of doing Euclid's extension and making your 1 with a linear combination of your A and B. Okay, so I'll leave this as an exercise to think about, what are the necessary conditions? Like how does this help us with division in the first place? If you can't figure it out, it's also in the textbook. It's a very beautiful proof. But the idea is, now not only do we care about this D, this greatest common divisor, we also care about this A and B. Right? We also care about the coefficients of these linear combinations that give us this greatest common divisor. So I want an extension to Euclid's algorithm that inputs A and B and outputs 3 things. I will output D, which is the greatest common divisor. I also want to output X and Y. Sorry, I probably missaid this. Not only do I care about this greatest common divisor, but I also care about X and Y. So these are the factors, the coefficients that make this linear combination work. Because we already know what A and B are, right? We already know what A and B are, so now we want to care about X and Y. Right? Sorry about that. X and Y. D, X, and Y. Alright. So I didn't make space to write down the whole algorithm. The idea is the exact same idea as Euclid's algorithm above. You'll just have to do a little bit more bookkeeping as to every time you subtract off this multiple y, you're going to update your A and B accordingly. So forgive me for not covering this. This mini lecture is already going to be extremely long. So if you're interested, make sure you read it in the book. But the idea is Euclid extension takes A and B and outputs the greatest common divisor and the coefficients that give the linear combination that equals the divisor. All right, I'll see you in the next section, primality testing. Let's talk about primality testing. So essentially this segment is going to follow the idea that you maybe learned in CS170 or some other cryptography class, that testing for primes is easy, but factoring things is hard. So we'll actually look at why testing for primeness is, I don't know, quote unquote easy. So before we jump in, let's start with a very famous theorem, Fermat's-Little theorem. Some of you might have seen this in CS170, others might have heard of it somehow, but it's this statement that if P is prime, if we're working over a prime field, then if I'm working over a field where, if we're let me say that again. If P is prime, then for every A between 1 and P, we have this condition that A to the P minus 1 is congruent, is equal to 1 mod P. What does this mean? So if I have P equals prime, then this condition, this sort of equation holds for every choice of A between 1 and P. That's just every number that's in this field except for 0. Right? Because 0, of course, you can't get to 1 mod P, but everything else can. Okay, let's quickly prove this. So we start with a set of all numbers that are non-zero. So I have 1, 2, all the way up to P minus 1. And I want to take the set AS, which is just every number in this set multiplied by A. So this is 1 times A, 2 times A, blank, 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 all the way up to P minus 1 times A. And a lot of these might end up reducing mod P. So I'm just going to keep them in this coefficient form. Okay. And something I need to realize is that I want to say these two sets are actually equal. Why is this? Both of them has P minus 1 elements, and the crucial observation is that all of the elements are different on the left side, and when I multiply them by the same number A, they must still stay different. Essentially what I'm saying is that if X is not equal to Y mod P, then AX is not equal to AY mod P, as long as A is not 0. This follows from the fact that P is prime, so every number other than 0 has these multiplicative inverses. So I can just take the multiplicative inverse of A and multiply on both sides. Okay. All right. So we've established that everything on the left is different, everything on the right is different. All the things on the left are just non-zero elements, mod P. And everything on the right is still the same thing, right? You don't change the elements. You can't get 0 ever. So we've established this equality, and the next step is we want to say, if I multiply both sides together, as in I multiply everything in the set S, and I multiply everything in the set AS. And these sort of products should be the same, because I multiply the same set of elements just in some different representation. On the right side, it might be just a little bit more scrambled than the left side, but they're the same elements. Okay? So I get 1 times 2 times 3 all the way up to P minus 1 is equal to 1 times A times 2 times A times 3 times A all the way until P minus 1 times A. So this is, if we pull all the A's out, we're going to get P minus 1 copies of A, and then we're going to get 1 times 2 times 3 all the way up to P minus 1. Now notice that there's this common factor, right? And then since we're working over mod P, as long as this factor is non-zero, we can find a multiplicative inverse, or basically divide by it, to get rid of it. And of course, when we're working over a prime field, if we're multiplying non-zero numbers, then we're not going to get 0. So this is going to cancel out, and all we're left with is A to the P minus 1 is equal to 1 mod P. And we're done. Okay, so this is Fermat's little theorem. It's very important because here's what we get, right? We've assumed that P is prime. So primeness is going to imply some condition on other numbers in the field. So condition on A, right? So maybe you're thinking, what if I take it the other way? What if I take, the converse of this? What if I just test some conditions on A and see whether that implies something is prime? So, sirens should be going off in your head because, you should be thinking, Lily, why are you lying to me? Theorems can't be reversed like this. And you would be completely correct. Theorems cannot be reversed like this, but we'd like to give it a shot. So in this primality algorithm intuition, we're going to try to give this a shot. What we're going to do here is, instead of starting with a prime P, we're going to test if P is prime by taking some A. So we're going to pick a random element A. We're going to pick A from this 0 to P, well, not 0 to P, 1 to P, and we're going to see whether this condition here actually holds for that particular A. So we're testing N, whether N is prime, all right? So we know that if n is indeed prime, then this is going to be true, right? So we say, okay, if this is true, then let's say n is prime. Okay? And if this is not true, let's just say n is not prime. Simple enough, you just reverse the arrows. If it's, if it works, it's prime. Doesn't work, it's not prime. Okay? And let's see how well this algorithm does. Because you should feel a little bit uneasy about this, because we're taking the arrow backwards. We're testing for primeness using this condition. Okay? So there are two ways of failing. One way is basically if n is actually prime and we conclude that n is not prime through the algorithm. So this one way number one is algorithm says not prime, but then actually prime. Right? This is the first way. And the other way is like symmetric to this, where the algorithm tells us it's prime and it's actually not prime. Okay? Let's look at each of these cases separately. So if in the first case, if p is actually prime, then our algorithm is always going to work. Because if n is prime, then this is going to hold because of Fermat's little theorem, right? Because this is exactly the statement that we looked at. If p is prime, then this holds. Okay? So this holds, and then our algorithm is always going to conclude that n is prime. So this first condition, this first case of failing, doesn't actually exist. We never fail this way, because if n is actually prime, then we're going to conclude n is prime through this algorithm because of Fermat's little theorem. This other case, however, is problematic. So we've essentially said, okay, if this is true, then we're going to call it prime. But perhaps you just got lucky in picking your a. There are some numbers, if n is a composite number, then it's completely possible that you have some lucky a that gives you this 1 mod n, even though n is actually composite. In fact, there's a class of numbers called Carmichael numbers in which every single a fails like this. But this is a very special case. It's incredibly rare, so you'll have a homework problem or a discussion problem on this. But if you're living in the real world, you probably won't be dealing with this all that much. So let's get rid of Carmichael numbers and see, okay, if our algorithm failed by identifying a composite number as prime, then it means there must be some a that fails this, right? There has to be some a that should give you not equal to 1, that should have classified n to not be prime, right? And so how do we know? How do we know how often this happens? How do we know how many different choices of a will end up making our entire algorithm fail, and how many choices will make it succeed? So this next theorem addresses this very problem. The next theorem says that if a to the n minus 1 is not equal to 1 mod n for some a coprime with n, so what does this if statement mean? It means that if our algorithm should have labeled n as not prime, right? If this is happening, our algorithm should have labeled it as not prime. Then I can say this is true for at least half of the choices of a. So at least half of the choices of a will cause our algorithm to label n as not prime. And that's good, right? Because we want, given some composite n, we want it to label not prime. So what this theorem tells us that based on the choice of a, we have at least 1/2 chance of getting an a that gives us the right outcome in the algorithm, right? Okay, if you need to pause the video and then mull over what this theorem is really saying, is that if I have a pool of a's, I have a bunch of different a's to choose from, I have at least a 1/2 chance of choosing such an a so that our algorithm will succeed in identifying n as not prime. Right. So the proof of this statement is very interesting. It's basically saying that for each, oh, wrong color. For each value b such that, I don't know, b to the n minus 1 is equal to 1 mod n, I have its twin, a times b, and I can say that a times b to the n minus 1 is not going to be 1 mod n. So essentially, like a value b such that b to the n minus 1 is 1 mod n, this is something that would cause the algorithm to give you a false answer. This would be something that if you pass in b, the algorithm is going to tell you that n is prime, but it's actually not, because we know that n is not prime. Right? For every b that makes the algorithm fail, we have an element a times b that makes the algorithm succeed, which means essentially that there has to be at least as many things that make the algorithm succeed as it makes it fail. All right, so you can think more about this at home, and this idea proves the theorem. I sort of hand wave this, but I'm going to reward myself with a little black box saying that I proved the theorem. It just says, given all my choices of A, if I just pick randomly, I have at least a 1/2 chance of getting an element of A such that my algorithm will succeed. Okay. And okay, so we have at least a 1/2 chance. So, but what if I think 1/2 chance is not a great chance? What if I want a better chance? Well, there's this idea in algorithm designing where I can just iterate, right? I pick many different numbers, many different choices of A, and if one of the A's gives me, not congruent to 1 mod n, then I already know that it's not prime, right? So you sort of accumulate the number of trials so that right, so that essentially, like at some point you're going to encounter something that makes the algorithm the algorithm give you the right answer. So here's the kicker. The probability that the algorithm returns prime when n is actually prime, we discussed this, is going to be 1. It always works when n is prime because of Fermat's little theorem. And the probability that algorithm returns prime when n is not prime is going to be smaller or equal to 1/2. We just proved this. Right? Okay. So what this means is that if I iterate this process many, many times, right? So I add one more line here. Probability that algorithm returns prime when n is not prime after n tries, or after k tries. What's this probability? It's a probability that every time you run this checker, our every time you run this checker, our algorithm failed, right? So like this is a failure, right? Not a prime. This is a failure compounding. You have to compound k failures every time you have to fail. If it succeeded even one time, we know that even if there's one A that makes this thing return not prime, then it's not prime, right? If it returns not prime, then we're done. So what this means is you do this k times, and you're going to get smaller or equal to 1/2 to the k. And this is just a probability sort of case. You might have seen this in CS170. I don't know how to explain this better. I hope this makes some sense. That if you have this trial that's going to fail at most 1/2 of the time, and you run this trial k times, then it's going to fail like 1/2 to the kth power times. You have to every time you have to fail, and these are all independent of this. Okay. So potentially you could have very, very, very good performance with this algorithm, even though we did this, unspeakable evil by reversing the arrow to the theorem. Okay. So the upshot is that the primality algorithm comes from the Fermat's little theorem by reversing arrows and trying to test for primeness using this condition on A. And then in the end, we got that this has a fairly good success rate.
Hi everyone, welcome to this week's 170 walkthrough. Today we're going to go over a question about independent set approximation. This is also a problem in your textbook, which is problem 9.4. Basically, the problem is asking for a given undirected graph where each node has a degree that is less than or equal to d, i.e. is connected to at most d other nodes within the graph, show how we can efficiently find an independent set whose size is at least a fraction of the largest independent set. We can call this the d+1 approximation, and it is dependent on the max degree of the entire graph. So that is a special property which gives us a possible approximation for this algorithm. Because as we all know, independent set it is very hard to solve, and it is an NP problem. But the thing is, if we have this very special property, then we can potentially find an approximation. A lot of times we want to find the maximum independent set. So in this case over here, we have by part type graph, everything on this left half is only connected to nodes on the right half. Independent set is where a subset of the vertices of a graph such that none of the vertices are connected to each other with an edge. So the way I would actually obtain this, since this is a small graph, is I pick vertices to delete. So in this case, if I delete this vertex over here, then I would also delete its edges. And then I keep deleting until I have like basically no edges left. And in this case, very simply, I get my optimal set just by like eyeballing. The optimal independent set is of size 3. And our algorithm supposedly should return to us an independent set of size at least 3/4. I know this doesn't make sense, and also this is much less, this is much worse than the optimal set for smaller graphs. But the approximation algorithm is used under the assumption that we are working with many vertices. So in this case, like even if it is a fraction of the optimal set that we get from our approximation algorithm, it still would be pretty good. So like what exactly is D, right? You might ask. So when D equals to the number of vertices minus 1, in which case we have a node that is connected to every vertex out there. That's a little bit tragic because if we were to somehow pick that one vertex, then our set that we get is just size 1. And we eliminate all the other choices because they're actually all connected. And there's no way to have an independent set of greater than size 1 if we were to pick that one vertex that has the degree of v minus 1, v being the cardinality of the vertices of graph G. Hopefully that doesn't happen. Or actually, here's an example where it does. So in this case, it's still pretty much considered as a sparse graph because it's like a tree, and just this vertex is really annoying if we picked it because, yeah, so if we have this vertex in our independent set, then we basically roll out all the possibilities of including the others. And in actuality, the optimal independent set is actually size 9, which is when we delete the middle one and we pick all the nodes that it's connected to. What our approximation algorithm does is that it guarantees that we find at least size 1, which is not, the best. But how can we maximize our probability of finding a set that is closer to the optimum? In the most extreme case, our entire graph could be our independent set, in which case we have something like this. So none of the vertices are connected with each other. So that is the best case. But this doesn't really happen. This is just not a well-defined graph, right? So we can probably use that in our calculations because the maximum, or we can basically upper bound our optimal independent set by the number of vertices in the graph. That might be useful later on. Maybe if we prove that our approximation algorithm could get us the fraction of total vertices in the graph, then maybe we're good to go. For example, if I want to prove that this is our optimal set is greater than size like this, I can prove that it is greater than something that is size beta, which is a greater number. And same with the other way around when you're trying to prove it is at most how much, like an upper bound, but you can also lower that bound. So you actually have a looser definition. But my intuition tells me that given these extreme examples, I might want to consider which one would be in favor of me at each step, i.e. each time I choose a vertex to include in my independent set. So here, if I were to choose a vertex, the vertex of maximum degree in this graph of degree d, then I end up with like the worst case. However, if I were to just pick the marginal vertices in this graph, I actually end up with my optimal, exactly my optimal, because you are avoiding this middle core monster. And in this case, like this is perfect because all of them have degree 0. So it seems like my algorithm of choosing vertices to put in my independent set would be best if my vertices are of lower degrees. So we're going to do exactly that. We are actually going to approach this problem greedily. And I know, like, even though NP sounds like very fancy and really out of reach for us at this point, we can use previous algorithms that we've used in this class to potentially, like approximate it. And that's exactly what we're going to do. So at each step, we are going to pick the vertex that is in V of smallest degree. And then we're gonna put it in our independent set. So our independent set starts out empty. Obviously, we got to pick something that is not already in our independent set. And again, by the smallest degree, I mean the least number of edges incident to that vertex, or the least number of other vertices that it is connected to. Because once we consider this one vertex V, let's call it V. Yep, that would help us name it. We cannot consider its neighbors anymore by definition of independent set. So why would this work? I think now is a great time to get into this, perhaps mathematically. So with most algorithm approximations, it's good to come up with an algorithm and more rigorously, perhaps with some inequalities, to show that our approximation algorithm really yields something that is a fraction of the optimal one. In this case, our independent set. So let's just examine our algorithm and think about some of the issues with like the size of our independent set versus the size of the graph that we have remaining after we picked some vertices already. Again, our approximation set is set I. So we want to prove that the size of our approximation set is at least 1 over d plus 1 of the optimal independent set, the cardinality of the optimal independent set. So going back to what I was saying, we can actually use what we talked about here. We can actually prove something even more maximum. So we can actually prove that the size of this approximation set is greater than or equal to d plus 1 times the size of the original graph. Because once we prove this obviously follows, because the size of your original graph it definitely has to be greater. So going back to this part of our algorithm over here, so for every v that we choose for our independent set, its neighbors must have been in the subset of the original graph that is not part of the independent set. So v minus I. What is this cardinality? This is the crucial part. Feel free to pause the video and work it out on your own here. By definition, the cardinality of v without I is just the size of v minus the size of I. So how many vertices are actually in this subgraph? Let's think about it. So this is where our condition that each node has degree at most d comes in. For every vertex that we choose to put in our independent set, it has at most d neighbors. So how many vertices have we chosen so far in the independent set? That's just the size of the independent set. And for each of these vertices, there are at most the neighbors for each. So we can actually upper bound this inequality like this. So the rest of it just follows. The rest is just like manipulating the inequality. So we can just say that the size of v is less than or equal to size of I plus d, which should be d times size of I, which is d plus 1 times size of I, which is our approximation set again. And you kind of see us getting closer to the approximation that in the problem statement. Okay, so this is how I want to manipulate my equation to be. So following that, I have size of I is greater than or equal to d over here, 1 over d plus 1 times the size of my original graph. And this is exactly what we wanted to show. And since this is definitely greater than the optimal set, we are finished. And that's it. So this is pretty cool. I think approximation algorithm problems are very elaborate because there are many parts to it, and there are many like small things. So first we come up with some examples that we walk through and sort of figured out what are some optimal ways we would try to find the largest independent set if we were to do it by brute force. And then we sort of concluded that picking smaller vertices or a smaller degree vertices would yield better results than picking a vertex of very large degree close to the maximum degree in the graph. And then so we came up with the algorithm like that. And we basically examined and analyzed our algorithm so that we were able to come up with this equation that relates the size of our optimal graph to the size of our vertex to the size of our approximation set and relating it back to this constant. And usually when they give you extra information, it's probably a big hint that we want to use it in our mathematical proof. That's pretty much it. So that's it for this problem walkthrough. Please feel free to let us know if you have any questions, and have a great rest of your week. Bye.
Hey everybody. So today we're going to be talking about clustering algorithms and their approximation form, which is what we're going to cover is k-means, is the approximation algorithm we're going to cover. So what is clustering? Why do we need it? Why is it so cool? I'm actually a big fan of clustering algorithms. I use them for a couple of my projects. And I'm sure you have too, actually. If any of you guys have taken E16A, what you do in that class is you build a voice-controlled car. And what you do is you apply a primitive speech recognition technique called principal component analysis, and then you do k-means clustering on that analysis. And I'll tell you what that means in a sec. So clustering algorithms means we want to define groups. We want to group these certain data sets or data points. So these data points can be either text entries or speech snippets, or I don't know, images, right? And we just want to group them together. And how we often like grouping them is to sort of split these images into certain properties and certain dimensionality constraints, and then plot them on a more graphical representation. So that could be a 2D, 3D, 4D graph, whatever. And then we sort of want to cluster them somehow. So that distance D algorithm between X and Y, we sort of want to minimize the distance between the center of each cluster and its neighboring points. So how do we go about doing that? Well, doing that is actually NP hard, and I guess you guys can sort of somehow intuit that it's kind of NP hard because NP hard as in it's in NP, and it's NP hard. That implies that it's NP complete actually. So this is actually an NP complete problem. And the reason this is NP complete is because we can actually reduce this down to vertex cover, which is like, as we know with reductions, if I can say that this problem is at least as hard as vertex cover, and vertex cover is at least as hard as set cover, and set cover is at least as hard as independent set, yada, 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 then we know that, okay, that's enough to prove that this is NP hard. So to prove, again, that it's NP hard, or to prove a reduction, actually, with vertex cover, we have to prove that a clustering algorithm, a solution in the to clustering implies a solution to a solution to clustering implies that there is a solution to our modified vertex cover and a solution to modified vertex cover implies a solution to clustering. So if we prove that, we prove a reduction. So let me just, and so that's a little bit of why it's NP complete. I'll talk a little bit more about that later. But if you leave now, just know that that's how we reduce it to. I mean, just know that we say that it's NP clustering is NP hard because it is a variant of vertex cover. Okay, so how do we get around this? What's our approximation? Well, fortunately, we have a pretty easy approximation algorithm for this for clustering, and this is called k-means. And what k-means says is, or k clustering, whatever. It doesn't necessarily need to be k-means, but for this example, we're going to illustrate with k-means. Essentially saying that if I know the amount of clusters I need to categorize, then this problem no longer becomes NP hard, right? So then it no longer becomes NP complete. So that's the algorithm, that's the approximation algorithm I'm going to be showing off today. And the book shows you sort of a two-dimensional exercise of it. I think it's also super easy and helpful to show a 1D solution to it. So let's go about doing that. So for our first step in k-means, what's going to happen is we choose a random point in this set of points, set of vertices here, or set of points, sorry. So I'm just going to choose a random point, eeny, meeny, miny, mo. Now I'm going to choose the farthest point from this point. So, and since this is 1D, it's super easy to see what our next point is going to be. Our next point is going to be right there. Let me mark it with a different color. So these are going to be what's called our centroids, or are the center of our clusters. So we go here and we cluster them here. And I'm going to label these center points U1, U2, and U3. And so now for U3, I want a point that is the farthest away from both of these. So what's the point here that's the farthest away from both U1 and U2 combined, i.e. maximizing the distance U3 between U1 and U2 and U3 and U1, the addition of those two distances. Well, that's going to be somewhere around here. It depends on sort of where this point is and this point, but and it depends on the relative distances, but I'm just going to say, for the sake of argument, it's going to be this middle point here, because that looks pretty nice. So there we go. All right, so now we have our three centers. This is called our partition, essentially, which means that we're sort of partitioning off our set of vertices into certain partitions. So like for this 2D plane, it would be like something like that would be our partition. So yeah, that's just saying that this is our partition here. So let's walk through the k-means algorithm together and sort of get you a better intuition on how it works. So let's start at U1 and move on. So at U1 here, we've got our center here, and we want to say, okay, this point here, this random point, what center do you belong to? Now, intuitively, you and I can sort of see that it belongs here, but what the k-means clustering algorithm is going to do is it's going to minimize the distance between all the centers U1, U2, U3 to UK, where K is the amount of clusters. Amount of clusters. Okay, so what's our distance to U2? Well, our distance to U2 is going to be right here. Oh no, that is absolutely massive. Our distance to U3 is going to be right here. And that's better, but our distance to U1 is going to be the minimum right here. That's absolutely small. So obviously this will belong to U1. And what we're going to do is we're going to keep doing the same thing over and over. For every single point that's unmarked or uncolored, we're going to keep doing that. So quickly, for this point here, what's going to happen? And pause the video if you want to now, and sort of figure out how is this point here going to be clustered. Like just walk through the steps. So let's go here and mark this point and say, all right, how's this going to be clustered? So pause the video real quick and go ahead and run through the algorithm yourself. 3, 2, 1. All right, hopefully you're back and hopefully you paused and did it yourself. So what's going to happen here is this is going to be its distance from U2, which is pretty small. It's nice. This is going to be its distance from U3. It's a little bigger, not that nice. And this is going to be its distance from U1. That's awful. So U2 is our best. It's going to be part of U2's group. So we're going to color this blue. And we're going to keep doing that for every single point in the set until we're done. So we go here. Let's color this here because of that. That minimum is right here. Bookmark it, move on. And just like that, we're going to keep coloring until we're done. So that's k-means in a nutshell. So I guess we can talk about a couple other properties of k-means, like how good of an approximation is it? And the way we want to do that is we want to show, so for this set of this more complicated set, let's just show a bunch of noise here, a point here. Let's say I wanted k to be 4 here and all the rest of this stuff is noise. Presumably I'd have a partition like this. So I'd start with any random point here. Hopefully I get lucky and get a good starting point. And so I'm going to start at a point here, maybe get this one, and then move on. Okay, I want the farthest from that. So I go like here maybe, and then I want the farthest from these two. So maybe here or something, and here. And then for each of these, I get a partition sort of like this, something like that. And then then clearly we'll have these clusters somewhat. It'll be something like that, or the cluster that's going to yield us. And all of these points will be put into the cluster. So one of the problems with this k-means clustering algorithm is k is fixed. So all of the points need to be clustered into a k. So if I have a point way out here that's really seemingly part of nothing, then it's going to be dragged in and it's going to ruin our nice variance and our variance that we're trying to minimize for this centroid right here, particularly. So with that being said, let's say so for this graph here, let's say we only want 4 clusters. So we've got our 4 points here, somewhere here, somewhere here. And remember, these points have to be in the set X, where X is big X, where X is all of our points. Okay, so let's then take this sort of selection algorithm one step further and find a point that is the farthest away from U1, U2, U3, U4 now, which is probably going to be this one right here. Well, what can we say about this point and this property here? We know that this point is part of a Now, the thing to notice about this point here is that it's the farthest. So we run our algorithm, right, where we choose our ui plus 1 point. And what does this mean? This means it's the farthest away from any of our points u1 through ui. So those are going to be our centers, right? And what does this mean? This means that this ui plus 1 point, which is our farthest away from all of these points, we only have k clusters here. We only have 4 clusters. We only have this, 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 and this. So that means that this point here is going to be part of one of these clusters. It has to be part of one of these clusters, which means that, so, and remember, this is the farthest point, which means that at most, and let's call this distance between this point and its closest centroid r. That means that at most, any centroid, any point in X, any one of these points here, here, or here, is going to be at least, I mean, at most, r away from the center, right? And what does that mean? That gives us a bound for the diameter of a centroid of 2r, right? So that means that any centroid is going to have a max of 2r. Or, sorry, less than or equal to 2r is going to be the diameter. Yeah, so that's the proof of sort of optimality there, where let's say like R is the sort of best we can do in terms of minimizing the distance for K clusters. That means that our centroid is going to be at worst 2R in diameter. So yeah, that's the proof of optimality there, and that's actually really good. It means that our solution is only going to be 2x worse than our ideal solution of clustering if we were to cluster it like ourselves with our eyes. So yeah, that's pretty cool. I hope you guys enjoyed this, and I'll see you guys next week. Thanks. Bye.
Hello. In this segment, I'm going to be going over local search, which is a technique for solving NP-hard problems by coming up with an approximate solution. So the idea behind local search is we're basically starting at some bad solution, so some suboptimal solution, and then we search for some nearby solutions, some nearby better solutions. So as an example of this, we're going to be looking at the traveling salesman problem. So as we recall, the traveling salesman problem is a problem where you're given n cities, and then you want to find a tour, which is a path that starts at one vertex and goes back to the same vertex, but also it needs to be one that visits every single city once, and we want to try to minimize the total cost or the total distance. So in total, there are n minus 1 factorial tours in a graph with n vertices. And that is a lot of tours. That is way too much for us to be able to brute force in most circumstances. So we need to come up with some approximation. And one way to do this is to first start off with some solution, and this can be just a randomly generated solution. So we might just come up with some random tour and then try to improve upon it. So how exactly do we improve upon it? Well, we need to define some sort of neighborhood. We need to define what nearby means. And so the neighborhood that we can use here is what we'll call a two-change neighborhood. So what does that mean? Well, we can think of two tours being similar if they share a lot of the same edges, except they might have only two edges that are different. That is what we might call a tour that is within a two-change neighborhood. So we are searching for tours that differ by up to two edges. And notice that two tours can't differ by only one edge, so two edges is actually the smallest neighborhood that we can really do, at least in a way that makes sense. So let's say we start off with this solution. Now this isn't really, you can see that it's not very efficient. It has all of these crossovers. But one modification we can make is we can say, okay, well, we have these two edges here, which if we replace those two edges with edges that go straight across this way, then that would be an improvement. We have a different tour that has a lower cost, a lower total distance. And we can, this is an iterative process, so we can repeat this. So let's say now we can remove these two edges and replace them with edges that go here. And now we have the optimal solution for this particular graph. Now, this isn't always going to happen. We're not always going to stumble upon the optimal solution. And I have another example down here where, let's say this is the graph that we start with, and we're still looking at the two-change neighborhood. Then we might, one thing we can do is we can take these two edges and then replace them with these. So we've changed two edges, so that's fine. But then now we're a little bit stuck. What we would love to do is we would love to take these three edges and replace them like this. So that way we have an optimal solution, but we can't really do that because it's not within our two-change neighborhood. We're not searching wide enough. So in this case, we would if we were doing a local search on a two-change neighborhood, we would be kind of stuck at this solution. And this is the solution that we would find, which is not optimal, but it is an improvement upon what we started with. So the nice thing about having a small neighborhood, having a two-change neighborhood, is that each iteration is pretty fast. We can see that every Tor has O of n squared neighbors. These are just the nearby Tors, the Tors that differ by up to 2 edges. So therefore, each iteration takes O of n squared time. So each iteration is pretty fast. Now, unfortunately, another drawback of local search is that we don't know how many iterations we're going to necessarily make. So we might end up making an exponential number of iterations, in which case our algorithm will be very slow. So that's another consideration to keep in mind. Sometimes you might want to limit the number of iterations or to have a stopping point where as long as you get a solution that's good enough, you might want to just stop there. But that's kind of the drawback of local search. It doesn't really provide any guarantees in terms of how optimal your solution is or how fast your solution is going to run. Now, remember that if we use two-change neighborhood, we're stuck in this situation. We can improve upon this by loosening our nearness constraint a little. So we'll expand our neighborhood a little. So instead of two-change, we'll call this three-change. A three-change neighborhood, which means that we'll look at other Tors that differ by up to 3 edges. So this gives us a wider neighborhood, which gives us more room for improvement. So we can see an example here. Now, if we started off with this Tor, one thing we might do is we might say, okay, let's see if we can improve upon this with a 3-change. So one thing we can do is, let's say we'll take these 3 edges and we'll replace it with an edge going here, an edge here, and an edge here. And then we can also, we can do a 2-change now. So we can replace these 2 edges with one going here and one going there. And then we can perform another 2-change where we can replace those 2 edges with this. And we can do another 3-change here where we'll take these 3 edges, 1, 2, and 3, and we'll replace it with this, this, and this. And I think we might even be able to improve upon this once more. We can take these 3 edges, 1, 2, 3, and replace it with 1, 2, and 3. Now, of course, this isn't the only way this sequence of events could have went through. You could have done this in any order, but you might have, but either way, you would converge upon some sort of solution. So you'll converge upon some point where there's no way to do better while only changing at most 3 edges at once. Now, this might not even necessarily be optimal. Sometimes you might even need to go 4-change, 5-change, etc. The problem with expanding your neighborhood is that each iteration is going to take longer. In this case, here, each iteration is going to take O of n cubed time, because there's n cubed other tors within the neighborhood of any tor. So this is going to be slightly slower on each iteration, but it's more likely to find an optimal solution. So here's kind of a sort of visualization of local search. You can think of this bottom axis as the set of solutions. Now, it might seem kind of weird to have solutions be represented on a one-dimensional axis, but this is just kind of a illustration, not really an actual graph. So you can think of this is sort of just a conceptual model. So you have solutions on the x-axis, and then on the vertical axis, you can have some cost or some sort of objective function that you're either trying to maximize or minimize. Well then, when we perform a local search, we might start off anywhere. We might start off here. So this graph represents the cost of the corresponding solution. So this would be our starting point. And then we iteratively improve upon our solution. We find a nearby solution with lower cost until we get to a point where we cannot do any better. And that is going to be our local optimum. Now, the problem with the local optimum is that it's not necessarily the optimal solution. It is optimal locally, but it's not necessarily globally optimal. And in this case, you can see that there's a solution down here where this is the actual minimum cost solution overall. This is the global optimum. So where you start will have an effect on which local optimum you run into. And if you're trying to optimize one, if you really want to try to get a good solution, one thing you might want to do is try to randomize your starting points, to try starting at many different randomized starting points, because that would increase your chances of reaching a better local optimum. Now, there are other methods. One method is simulated annealing, which can let you avoid bad local optimum. But in general, these are just sort of heuristic techniques, and they don't really provide any guarantees as to the runtime or how optimal your solution is. Nevertheless, local search can be very useful when you're trying to find a solution that's good enough, but isn't necessarily going to be the optimal solution.